Hello, everybody. So this is week 8, and this is the first part of lecture 1 of week 8. And we're starting today on chapter 5, which is sampling distributions. And this is the beginning of the statistics part of this course. So with no further ado, let's switch over to the notes. So as I mentioned, this is chapter 5, sampling distributions, and we're starting in on statistics. And basically, we're relating our theoretical models, which we've been discussing up to now. So theoretical, continuous, or discrete distributions. Now we're relating those to real data. For this, we need some definitions. We're going to talk about populations. So this is the entire group of objects. These will be random outcomes of experiments that we are trying to describe. A sample is a collection of observations from the population. And the sample space, of course, would be the complete collection of observations from the population. Most importantly, we're going to define something called a random sample. And this is a sample of observations, which I'm going to call x1 through xn. And once I've made the observations, these are lowercase, so they're known values. Before I've made the observations, they're uppercase, and so they are unknown before I've done the experiment. But the main thing to remember about the definition of a random sample is that the observations are assumed to be independent from one another. Okay, we need this, well, we don't need it, but this vastly simplifies our life when it comes to statistics, because if it's from a random sample, the independence means the variance of a sum becomes sum of the variances. Statistic itself is going to be a function of our sample observations. So examples of statistics you've already seen, and basically we're only going to consider the two common statistics. One is the sample mean, also called the average, which is defined as x bar equal 1 over n, sum of the xi's, sum of my observations. As I mentioned before we've observed the samples, they are random, so I'm going to use capital X's to denote the values of my observations before I've observed them, and those values, of course, are unknown and therefore random. And that means x bar is also random. And so we can talk about the distribution of this x bar. We talked about this a little bit in the last lecture of week 7, so our previous lecture. After we've observed the samples, they become realizations, and the x's turn into lowercase x's. So these are actual values and actual numbers. So x1 might be 2.3, for example. And our x bar also becomes lowercase. So this becomes an actual realization of capital X bar. Sample variance is another statistic that we're going to talk about. Usually I'll subscript the sample variance with the thing that it's governing. So this is s of x squared. S sub x of, so the variance of x basically is 1 over n minus 1, sum I equals 1 to n of xi minus x bar, quantity squared. And again, if we haven't yet taken our observations, these x's are random, and that means the s is also random, so we can talk about the distribution of this. And we saw that after some normalization, this becomes chi-squared distributed, and this x bar becomes t distributed if the sigma is not known. So basically, again, once we've taken our observations, capital S becomes lowercase s, and I can again put that subscript x in here. To denote the variable that it's the sample variance of. Okay, so let's look more carefully at the sample mean. Again, this is defined as x bar equals 1 over n times the sum of the xi's. And this tends to a normal distribution by virtue of the central limit theorem. But we'll generally assume that the x's are already normally distributed, so that x bar is exactly normally distributed. And the reason we do this is we'll see later, if the sigma is not known and we replace it with s, the s itself only follows a chi-squared distribution if the x's are normally distributed. And in fact, x bar standardized by subtracting the mean and dividing by s over root n only follows a t distribution if the x's are normally distributed. Okay, so if in any case, if x bar is normally distributed, then we need to find mu x bar and sigma x bar, and we did this also in the last lecture. We found that mu x bar is just equal to the mean of x, and therefore x bar is an unbiased estimator of the true mean. And by unbiased, I mean, is this estimator aimed at the proper thing? So on average, does x bar aim at mu of x? And this calculation here shows that it does. Okay. So in other words, the mean of the average is just the mean of the population, and that makes sense. For the variance, we assume a random sample so that the x's are all independent. Then the variance of x bar, it becomes the variance of a sum. The 1 over n comes out front and is squared because this is the variance. And then variance of the sum of xi's becomes the sum of the variances because we've assumed that the xi's are all independent. So we get this variance of x bar is 1 over n squared times the sum of the variance of the xi's. These are all sigma x's. So I got n sigma x's, and I forgot a close bracket here. And so I got n sigma x squared divided by n squared. So sigma x bar is sigma x squared divided by n, or the standard deviation of x bar is sigma x over root n. Note that as n goes to infinity, then the standard deviation goes to 0. In other words, the standard deviation of x bar, if it goes to 0, it means x bar becomes deterministic. And in fact, it does become deterministic and equal to the true mean. Okay? Okay, so now if we want to compute probabilities relating to x bar, such as the following, we just need to follow our usual process for normally distributed random variables. So the probability that x bar is less than a, x bar is assumed to be normally distributed, so the first thing we do is standardize, subtract its mean, divide by its standard deviation on both sides of the inequality. This thing here, of course, is z, so this brings us to this cumulative standard normal distribution of a minus mu of x divided by sigma x over root n. Let's illustrate this with an example. Let's suppose an electronic company manufactures resistors that have a mean resistance of 100 ohms and a standard deviation of 10 ohms. Find the probability that are random. By the way, if you were buying these resistors for an electronic component or device, you probably wouldn't like these resistors very well because they got a pretty high standard deviation. Normally, resistors would have a much lower standard deviation. They'd still be a little bit, not quite 100, but they would probably have a standard deviation well less than 1 ohm. But I've set it to 10 ohms just to sort of make this a more random quantity. Find the probability that a random sample of 25 resistors will have an average resistance less than 95 ohms. Okay, so I'm talking here not about an individual resistor, but the average of 25 resistors. What is the probability that the average is less than 95 ohms? So let's let x equal the resistance of a randomly selected resistor, and we're told that we're going to sample 25 of these resistors. Each of them has mean 100 and standard deviation 10, and we want to find the probability that x bar is less than 95. Well, we're assuming x bar is a sum of x's. Even if these x's aren't truly normally distributed, their sum will tend to a normal distribution by the central limit theorem. So this thing can be approximated by normal, so our next step is to standardize. We subtract its mean, divide by its standard deviation on both sides. We know the mean of x bar is just the mean of x, and we know the standard deviation of x bar is just sigma x over root n. So I know everything inside here. Just substitute in the 100. 10 divided by root n is root 25. I get 5 minus 2.5. 5 minus 2.5 is on the wrong side of my probability standard normal probability table, so I have to flip it over. This is just equal to 1 minus 5, 2.5. Here I looked this up on the table. I get 0.99379, and 1 minus that, it gives me 0.00621. Okay, here's the illustration. Phi of minus 2.5 is the same, so that's the area below this, is the same as the area above 2.5, and that area is 1 minus the area below. Okay, so 1 minus phi of 2.5 is this area above, which is the same as this area down here below. If we look so this is the probability that X bar is less than 95. It's a pretty small probability. If we look at the probability that an individual resistor is less than 95, that's what we're computing here. Well, we take, we'll assume this is normally distributed, subtract its mean, divide by a standard deviation on both sides. We end up with phi of minus 0.5. If we look at our, that's 1 minus 5, 0.5. Look at our tables, that's 1 minus 0.7 approximately, which is about 0.3. So the probability that an individual resistor is less than 95 ohms is about 30%, which is way bigger than the probability that the average of 25 is less than 95. Okay, just to emphasize that. In other words, averaging reduces variability. So instead, this one had a variance of 10, whereas this one actually has a variance of 10 divided by root 25 is 5, so it's 2. So this one has standard deviation, which is 5 times smaller than the individual variability. And that leads to this much smaller probability that we're less than 95 ohms. Okay, let's look at another example. Let's suppose a PVC pipe is manufactured with a mean diameter of 1.01 inches and a standard deviation of 0.003 inches. So this is actually another one of these quality control type questions. The mean diameter presumably is what we're aiming at. The standard deviation, we want to make this as small as possible in our manufacturing process. And this is pretty small relative to that mean diameter, so maybe that's not too bad. But what is the probability that a sample of 9 pipe sections will have an average less than 1.009 inches or more than 1.011 inches? Okay, so again, I'm looking at the average. So the probability that average is outside some range around what the mean should be. So we're told that we've got n samples that we're going to average. The mean of each is 1.01 and standard deviation is 0.003. We hope that xi is at least approximately normal so that x bar can be assumed normally distributed with mean of x bar is the same as the mean of x, which is 1.01, and the standard deviation of x bar is sigma x over root n, which is 0.003 divided by root 9, which is 3, gives me 0.001. So we're looking to find probably that x is less than 1.009 or, x bar is less than 1.009 or x bar is greater than 0.011. I see a union here, so I ask, are these disjoint? Well, if x bar is less than 1.009, it can't also be greater than 1.001, so they are disjoint. That means this union becomes a plus sign, and I'm just looking at the probability that we're less than 1.009 plus the probability that we're greater than 1.011. Then basically these x bars are normally distributed, so I standardize both of these terms by subtracting the mean and dividing by the standard deviation of x bar. Standard deviation of x bar was this 0.001, and I get these two terms. It turns out that these 1.009 and 1.011 is symmetric around the mean of 1.01. So this is the probability that z is less than -1 plus the probability that z is greater than 1, which is just twice one of the probabilities. Let's take this one here. So this area here is 1 minus phi of 1, and this area down here is the same thing. So the probability that I'm looking for is 2 times 1 minus phi of 1, which gives me 0.32 approximately. Let's illustrate it with another example. Let's suppose the random variable x has a continuous uniform distribution. X is f of x is 0.5 if x lies between 4 and 6. So what does this thing look like? Here's my axes. Oops. And this is f of x. And this is x. And basically this thing looks like this. This is 4. Oops. And this is 6. And this is a half. Okay, so this is uniformly distributed, so it's equally likely to occur between 4 and 6, and then it's 0 outside that range. And that's what our distribution looks like. Let me just see if I can clean this up a little bit. Oops. 0.5, okay. Okay, find the distribution of the sample mean of a random sample of size n equals 40. So sample mean is the average of a sample of size 40 from this population. One can calculate from f of x that the true mean is 5. Okay, so from this distribution, the true mean is the balance point, which is halfway between 4 and 6, which of course 5. And if you recall, the variance of a uniform distribution is 1/12 the width squared. The width here is 2. So this is 2 squared divided by 12, which is 4/12, which is 1/3. Okay. Okay, so we know the sample mean is x bar is the sum of the xi's divided by n. In this case, it's a sum of uniforms. The actual distribution of a sum of uniforms has no known, at least common distribution. However, for 40 terms being added up, the central limit theorem tells us that x bar will be very nearly normally distributed, and its parameters will be the mean of x bar is the mean of x, which is 5, and the standard deviation is the variance is the variance divided by n, which is 1/3 divided by 40, which is 1 over 120, and so the standard deviation is the square root of the 1 over 120, which is 0.091287. So that is the distribution of the sample mean of a random sample size n equals 40. Mean is 5, standard deviation is 0.0913. However, we note that x bar must actually be bounded between 4 and 6 because all of the terms that lead to its sum are also bounded between 4 and 6. The normal distribution range is minus infinity to plus infinity, so this thing cannot be truly normally distributed. However, the normal approximation, if we look at the probability that we're outside one of the bounds, let's look at the probability that x bar is less than 4. We get, this is minus 1 over 0.0912, which is a phi of minus about 11 standard deviations. So 5 minus 11. If we plug this into some sort of sophisticated calculator, we find that this probability is around 3 times 10 to the minus 28, which is extremely small probability. And similarly for the probability that x bar is greater than 6. So this is actually a pretty good normal approximation. Very, very, very small probability of lying outside the range that it can't lie outside of. Okay. The above calculations assume that sigma x is known. So when I was standardizing, I was dividing by sigma of x bar and replacing that with sigma x over root n. However, if the sigma x's are unknown and estimated by our sample variance, which is 1 over n minus 1, sum I equals 1 to n of the squared deviations from x bar, and this, of course, you'll recognize is an estimate of the true variance. And the true variance is the expected value of this squared deviation. We're basically approximating this expectation as 1 over n minus 1 times this sum. So expectation is an average over all possible values, and this is also an average. The difference being that we're replacing the true mean here with our estimate, x bar, and that's why we get n minus 1 here. But basically this average is an approximation to this true mean. Okay, so if I replace sigma with s, then I now get this t distribution random variable. And it's equal to x bar minus mu of x divided by s over root n. And now we've got these two terms that are both random contributing to the randomness in t. And so it's going to have a wider distribution than z. And we saw this in our last lecture. It turns out that this quantity t follows a t distribution with nu equals n minus 1 degrees of freedom. And I showed a picture the other day. If this red one is the tallest one here is the z distribution, that's the standard normal, then the t distribution is wider. And if, for example, if the number of degrees of freedom is 30, the t distribution is going to be reasonably close to the standard normal, but a little bit wider. And then if as the number of degrees of freedom reduces, the t-distribution becomes wider and wider. They're still all centered on 0, so they still all have mean 0, but they become wider and wider as the number of degrees of freedom reduces. Okay, so if we look in the summary pages, we'll see values for the t-distribution in the second last table. This is an inverse table giving values of t, alpha, comma, nu, having area to the right of alpha. In other words, the values in the table are these numbers along the horizontal axis, having area to the right equal to the value of alpha. Let me just quickly go and illustrate that. So if we go to our summary pages, let me just make this bigger. So this is, so this is the t-distribution right here. Okay, so this is the values of these little t's that give us area to the right of alpha. So if we're looking for a value having area to the right of 10% or 0.1, when the number of degrees of freedom is 9, we see that that value is 1.383. So the probability that my t with 9 degrees of freedom is greater than 1.383 is equal to 0.10. Okay, let's go back to our question, our notes. And we see example. Okay, so let's look at an example. Probably the t 0.05 with 10 degrees of freedom is greater than 1.182 is equal to 0.05. And this is for nu equals 10 degrees of freedom, so n is 11. Let's go check that. So we need to remember, we're looking at area to the right of 0.05, 10 degrees of freedom, and 1.812, and just checking to make sure that that area is 0.05. So I'll go back to my summary pages. Make this big. And we've got 10 degrees of freedom. Area to the right of 1.812 is 0.05. Okay, so everybody see where that's coming from? Okay. Go back here. Oh, shoot. Okay, I gotta stop. So I'm stopping here. The camera just turned off. Actually, maybe I won't stop. I just won't say goodbye this time because my camera died. So back to my notes. Okay, so that's probably t is 0.05, comma 10 is greater than 1.1812 is 0.05. Also, I noted the other day that when n goes to infinity, the number of degrees of freedom also go to infinity, and t collapses to the z distribution. And this is the last line of the t-table, and we can use that to find values of z sub alpha. So if you're looking for values on the horizontal axis of the z distribution, of the standard normal, with area to the right, remember it's area to the right, of alpha, you can use the last line of the t-table. Okay, so let's conclude with another example. Let's suppose a manufacturing firm claims that the batteries used in their electronic games will last an average of 30 hours. To maintain this average, 36 batteries are tested each month. If the computed t value falls between t minus t 0.025 with 35 degrees of freedom, so that's n minus 1, and t 0.025 with 35 degrees of freedom, the firm is satisfied with its claims. In other words, what they're going to do is they're going to sample 36 batteries, compute an average lifetime, and then they're happy that their claim is correct if that lifetime isn't too far away from the claim. Okay, in other words, if it's less than t standard deviations away from the claim. Okay. What conclusions should the firm draw from a sample that has sample mean x bar equals 27.5 hours and sample standard deviation of sx equals 5 hours? Assume the distribution of the battery life to be approximately normal. Okay, so what are we doing here? We see 27.5 hours from a sample of 36 batteries suggests that the true mean lifetime is actually less than 30 hours. So let's just see if it falls outside of this range. Okay, so we know n is 36, x bar is 27.5, and s sample standard deviation is 5. Since we do not know the true sigma x, we must be dealing with the t distribution. If the t value falls between these two numbers, then the firm is happy with its claim. So what are these two numbers? T 0.025, comma 35 degrees of freedom. Let's go back to our summary pages. So remember this, we're looking for area to the right of 0.025, and we have 35 degrees of freedom. Okay, so we look at our summary pages. I'm looking for 35 degrees of freedom. I don't see it. I do see 30 and 40. And let's look at the column which says 0.025 is the 1, 2, 3, 4, 5th column. So this column here. And I want to be between 30 and 40. So the number I'm looking for will lie somewhere between 2.042 and 2.021. I would guesstimate 2.03 would be a good number to use here. So back to my notes. Let's see what we have here. Okay, so these numbers here, we don't know what they are exactly, but we saw 30 degrees of freedom, t of 0.025 was 2.042, and 40 degrees of freedom, t of 0.025 was 2.021. And so, as I said, I'm going to guesstimate that the t value that we're looking for is 2.03. And this basically means that we want our sample mean, x bar, to lie within about 2 standard deviations from the true mean. Note that these numbers here get closer to z of 0.025, so the area, the z value with area of, to the right of it is 0.025 is 1.96. So this is narrower distribution. It's a slightly smaller number than this, but if you look in the table, you see that, these numbers here get closer to 1.96. You see this number is closer than this one, to 1.96, as the number of degrees of freedom gets larger. Okay, so let's just check to see if we've satisfied, if the firm is happy with its claim. X bar is 27.5. The mean is, the claim mean is 30. S is 5. N is 36. So I get t, my t value, which is the number of standard deviations x bar is away from the mean, is 27.5 minus 30 over 5 over root 36, which is minus 3. And this is further away than 2 standard deviations. So basically it means that the firm is not happy with their claim. There must be something going wrong. They've got to improve their workmanship or the quality of their product. Basically, x bar is 3 standard deviations away from where it should be if the true mean is in fact 30, and this is unlikely to happen. But may happen with a probability 0.0025, which is a pretty small probability. So there seems to be something wrong with this batch of batteries. Okay, well that ends the first part of lecture 1 for week 8. I'm afraid my camera has died, so I can't say goodbye in person. I will say hello shortly in the second part of lecture 1. Okay, so thanks everybody. Talk to you later.